Hi, I am Ahsanul Kabir and our work is ORDSIM, Ordinal Regression for E-commerce Query Similarity Prediction. I am presenting this paper on behalf of my team. In this presentation, we will first describe the necessity of similar queries and then how the dataset is created for supervised similarity prediction task, and also the necessity of these. And finally, we will define ordinal regression and why ordinal regression is necessary for this kind of similarity prediction task. E-commerce queries are not like web queries, and e-commerce queries are sometimes shorter. Sometimes the queries are consist of product properties, which does not match with normal web queries. And a single query, I mean e-commerce query alone sometimes does not capture the intent of buyer. So that's why the token level similarities are not enough to capture the actual representation of e-commerce queries. Sometimes other associated properties are also important. uh, to state the usefulness of our current work, we can say that the similar queries are very important in e-commerce domain for related sources, and sometimes query expansion can be performed, and recovery from zero or low recall. That means some products, some queries do not have enough listings associated with that. So to recovery from that, we need the similar alternative queries to suggest user with right spelling, and auto completion of the queries are also important in e-commerce domain. At this stage, we will describe the necessity of supervised query similarity prediction task. Note that we call two queries similar when both queries will find similar titles in an e-commerce site, and those titles will be used to find the embedding of these queries. And for that, two queries will be first randomly chosen from user log, and these two queries will have associated titles, and these titles will be embedded and mean pooled for the query embedding. And then uh, the cosine similarity is calculated between the queries. So the expectation of the supervised method is that it will capture the relation of similar queries, and it will find similar queries for unknown queries, so that recovery from zero recall or almost zero recall can be performed. So the dataset has three columns. The first one is for query A, the second one is for query B, and then the third one is the similarity value between these two queries. Alongside that, a category tree is there as well. The category tree has some nodes, and note that when anyone starts with some e-commerce query, every query will fall into some category. Say maybe someone is typing Nike shoes, so Nike shoes will have find its corresponding category, that is clothing, shoes, and accessories. So in that way, every query will find its associated category. So that category tree is another option for us, whether to include that in the query representation or not. And the master dataset has 10 million entries. We split the dataset into train, test, and validation. But I mean, all the train, test, and validation datasets are designed. We maintain 6:2:2 ratio, and the data is chosen randomly. And then for query embedding, we use BART and spherical text embedding. For categories, we use BART spherical text embedding, and then we also use point care embedding, as the point care embedding is better suited to represent the tree structure. So when we try to rank the highest queries, we find that the high similar queries will be congested in a narrow space. So you see that although there is no absolute cutoff, but if the similarity value is less equal 0.95, we will find some irrelevant queries. For example, between USB-C to Lightning to USB-C adapter, these two queries are not uh, similar, but the most similar queries will have better similarity scores, that is more than 0.95. So the other queries like USB-C to Lightning cable and USB-C to Lightning, these two queries are very similar with this USB-C to Lightning. So the key point is that at very high similarity values, the ranking is very critical. Recall that the most similar queries are very congested. So the histogram is showing that also. So 36% of the similarity values are between 0.95 to 1. That means 36% of our data are in this band. We can allow mistake in the lower similarity values, but we cannot allow mistake in the higher similarity values. That is why ranking of similar queries are very difficult in this narrow band. That's why the bucketing is necessary. So it is important to find the right buckets for query pairs. In this task, we have defined 5 buckets, and between 0.97 to 1, we have the most similar query pairs, and then between 0.95 to 97 we have the similar query pairs, but still uh, those are not most similar, but still those are important. But between 0 to 0.95, these queries are not as important in terms of similarity as the other two we just described. So you see, this problem is kind of some ordinal regression problem, because if we convert each bucket to a ordinal level, say from 0, from 0 to 0.82, it will get ordinal level 0, and the highest similar bucket will get ordinal level 4. So the most important queries will be in level 4, and the second most important queries will find level 3. So if the model cannot predict 4 when the actual level is 4, it is expected to predict at least 3. But if it predicts 0, that doesn't make sense, because 0 is for the least similar queries. So you see, the normal classification or regression task cannot capture that. So for normal classification, if the actual level is 3 and the model is predicting 0 or 4, the model will get same error, same constant error. But that is not the case with ordinal regression. So predicting 4 is better than predicting 0 in ordinal regression, because 4 will be nearer to level 3 than 0. Again, for regression, if the actual similarity is 0.95, it belongs to level 2. If the model is predicting that as 0.96, it will get only 0.01 error. But in ordinal regression, the level error will be 1, because 0.95 belongs to bucket 2 and 0.96 belongs to bucket 3. In this work, we compared with Coral as one of the baselines which perform ordinal regression. So like us, it also uses the last layer of a neural network. If we have L different ordinal levels, the Coral will produce L-1 channels, and if the actual ordinal level for an instance is P, it expects that all the output channels from 1 to P minus 1 will produce a value close to 1, and the remaining output channels will produce a value close to 0. To achieve that, it uses binary cross entropy loss in each of its channel. So Coral model is one of the best in the literature, but still it has some limitations. For example, in our current bucketing system, we have 5 ordinal levels and 4 output channels will be provided by Coral model. So if the output channel has output 1100, it will be interpreted as 2. Say the 2 queries belong to the most similar bucket, that is level 4. So the actual output is 4. So the Coral model is expected to predict as 1111. But say the second channel has some error. That means the output is now 1011. But this value will be interpreted as 1. So there will be level error of 3. And it has done a huge mistake in the most similar bucket. So we want to overcome this in our ORDSIM model. So in this slide, we will describe our ORDSIM model. You see, ORDSIM works with a neural network, and the last layer of the neural network is modified for ORDSIM. So from the diagram, you see that 2 queries, Q1 and Q2, will be embedded first, and both queries may have categories associated with that, and the embedded vectors will be passed into a neural network, and finally the output layer will be modified, and we have some defined loss function. That is, the loss function captures how far one predicted similarity value is from its actual bucket. For example, the actual similarity value is 0.97. So from the buckets, recall that 0.97 belongs to the bucket 0.95 to 0.97, and the median of this bucket is 0.96. So if the predicted similarity value is 0.955, that means it is 0.005 distance away from the median of its actual bucket. So the squared error will be square of this value. So at this stage, we will present our result. So note that linear regression cannot perform ordinal regression directly. That's why we needed to convert the predicted continuous values of linear regression to ordinal level. So all the predicted similarity values are converted for that, and with linear regression, spherical text embedding performs the best. That has the best mean average level error, that is 0.923. Note that spherical text embedding is our best query and category representation method, because with all configuration, with all the baseline methods, spherical text embedding performs the best. In terms of baseline methods, our method ORDSIM performs at least 42% better than the previous best method. So the Coral ordinal model has the mean average level error 0.781, which is the second best, and our ORDSIM not only performs best with spherical text embedding, but also with other embeddings as well. So in this work, we have explored different embedding methods, different representation of queries and categories. We performed point care embedding for categories, and we see that due to a space mismatch issue, that representation does not work well. But when we represent in a spherical space for both query and category, as both are embedded in similar space, this performs the best. And in terms of similarity, spherical text embedding is the winner because it can capture similarity better than eBERT. and we have achieved substantial improvement over baseline methods for the embedding task and a query similarity prediction task. Also, we want to introduce some method for our future work which will perform better when there is embedding mismatch issue as well. We want to improve query processing and other search use cases as well.